morning. I think in the class today we will extend a little bit of what we did in the last class, namely look at the reaction of hydrogen and oxygen to form water. Why I say we look at this example is when we use hydrogen as a propellant, it is not as a gas, it is at a very low temperature. Similarly, oxygen is at a low temperature. We use hydrogen at a temperature, if it is to be a liquid, at 20 K, oxygen at let us say 80 K. Our interest is to determine what will be the temperature of water which is formed. And mind you, as per this reaction is H2 plus half O2 is equal to H2O. When the initial condition of hydrogen and oxygen is not standard, then there is some change. Therefore, maybe let us do this problem. But before we do this, let us again be very clear of our summary of events what took place in the last class. We told ourselves, well, the value of C star is maximum when the mixture ratio is less than mixture ratio stoichiometric. That means in this region of fuel rich condition, that means fuel rich, you have higher value of C star compared in the oxidizer rich condition. It is very rare, it is almost impossible to operate an engine under oxidizer rich condition because you have higher molecular mass and you do not get the advantage of temperature either, and therefore we normally choose compositions which are fuel rich. But maybe before I go to this problem, since we studied what are the conditions required, let us just put down some 5 or 6 propellants which we can say are viable propellants. One is we say, oh yes, hydrogen and oxygen to give me H2O, but I want to operate it under fuel rich conditions, therefore I will get something like H2O plus H plus O plus OH and so on, because I get H because it is I do not have sufficient oxidizer to form water, and these are my products of composition which I will get. Therefore, I say, well, hydrogen oxygen could be one of the propellants, and let us do a small problem under stoichiometry and then extend it to fuel rich condition. The other propellant we said could be hydrazine N2H4, we said oxidizer could be nitric acid HNO3, or better still, compared to nitric acid we said N2O4 had a small positive value, therefore hydrazine and N2O4 is a good combination, and this would again give me maybe some products. Why not we think in terms of kerosene? Kerosene had a large negative value, but not very large either, it was something like minus 200 and odd, and you had oxygen, it gives me products, again I choose fuel rich condition. Well, this could be a candidate which we could have. You find that these substances like nitric acid, maybe N2O4 are widely used as oxidizers, hydrazine is also used, and we will see the advantages of using hydrazine with this. Instead of hydrazine, I could have something like N2H4 which is hydrazine. I remove one of the hydrogen atoms here, I have N2H3, I substitute it with a methyl radical, it becomes as one methyl with hydrazine, it is known as monomethyl hydrazine, and this is a very popular propellant combination, monomethyl hydrazine plus N2O4 giving me products of combustion. Mind you, we will again keep it to be fuel rich, not oxidizer rich. Like this we can keep on adding. Most of these things are maybe gaseous propellants, I could liquefy it and use it as a liquid propellant, these are all liquids. We could have solids, and what could be the solid? We say I could use something like let us say we had ammonium perchlorate which was an oxidizer plus aluminium, plus we also told ourselves in the last class maybe nitrocellulose could be used, or else polymer could be used, and you know we normally do not combine ammonium perchlorate, aluminium and nitrocellulose, or rather we combine nitrocellulose and nitroglycerine to give me a propellant, and we combine ammonium perchlorate plus aluminium plus polymer to give me a solid propellant. Well, the selection is somewhat limited, we can't have infinity, because based on the criterion we have laid down, we said yes, this becomes something like a double base, 2 bases, each one could be a propellant, but this could be a propellant, or I could have composite of ammonium perchlorate, aluminum and polymer to give me something like a solid propellant. If I think in terms of hybrid, well, I take the polymer, I cast it over here, I allow the acid to fall on it, liquid and solid, and this gives me what we call as a hybrid propellant. And again we make sure that the rate of reaction is such that it will still be fuel rich, such that I get a high value of performance. This is all about propellants per se, but I think we have to get into some more depth of why, if the initial conditions are different, how do you get the temperature of this. But one thing which I forgot to mention in the last class was, if I have pressure in the chamber, like let's consider the following. I have a chamber in which chemical reactions are taking place, and supposing I have high pressure, very high pressure here. If I have high pressure in a chamber, the amount of dissociation what takes place, that means dissociation is maybe CO2 becoming CO plus O, or rather let us say CO plus half O2 or CO plus O, or let us even say CO plus O. You know, if I have high pressure environment, I cannot increase the number of molecules. To make something dissociate at high pressures is more difficult than at low pressures, because what does pressure do? It tries to reduce the volume. That means if I have to grow the volume because molecules are increasing, I essentially need low pressures. Therefore, I have still not considered the effect of pressure, it must come from dissociation. But having, even without doing this, let us see some results on what will be the effect of, let us say, dissociation. All what I am trying to say is, a dissociation reaction, what do we mean by dissociation? We are talking of breaking up. What is breaking up? Maybe water breaks up into O plus OH. Why does it break up? The temperature is so high, it has so much of energy in it, it tries to break up. Similarly, I have CO2, it is trying to break up into C plus CO plus O, let us say. You know, when will this breakup be possible? At extremely high temperatures, at the temperatures in which maybe we are operating. But more interestingly, if I have a high pressure, the pressure will try to snub this reaction. Amount of dissociation would be much less at high pressure than at low pressure, because at low pressure the ambient pressure is small, something can dissociate and multiply. At high pressure this is not possible, and therefore I find that high pressure the dissociation is small, if the dissociation is small at high pressures, well, energy is not lost in this dissociation, Tc will be higher. Not only dissociation, but since dissociation is small, the molecular mass will also be large, but the effect of Tc is much more dominant, and therefore maybe it still has an effect on C star. Let us take a look at the result before I do the theory part of it. You know, here I plot the temperature of the products of combustion as a function of mixture ratio for a fuel rich hydrogen oxygen mixture at a pressure of 1 MPa, 10 MPa, 100 MPa and 1000 MPa. You find that at a given mixture ratio, as the pressure increases, the temperature increases, because at high pressure the amount of dissociation is less. We have to find out why. We will do a problem. You also find that the molecular mass of gases increases with mixture ratio, but also we find that as the pressure increases, the molecular mass increases. Why is that? At higher pressures you have less dissociated gases, and dissociated gases have a low molecular mass, right? Is it clear? Let us go to the next one. If now I say the value of gamma, we said gamma is higher for the monoatomic species 1.67 for helium, for very complicated CCl4 it was 1.18 or something, 1.13. Therefore, you find that as the chamber pressure increases, the dissociation is less and therefore the gamma value is smaller, and of course with mixture ratio we have already seen the variation of gamma with mixture ratio. If it is more oxidizer rich, you have heavier products which are formed and therefore the gamma is decreasing, but more importantly now we are considering the effect of pressure. As pressure increases, the value of gamma decreases. Why is that? Because I have more complicated molecules, dissociation is less. And now if I put all the things together, I find my effective C star or equivalently the ISP, because ISP is equal to C star into the nozzle performance is equal to, you find that as pressure increases, the optimum value of the mixture ratio for which I get the maximum value of C star keeps changing. Therefore, there is, it is not only just the mixture ratio alone which decides it, but the pressure is important because pressure influences the amount of dissociation. This is for hydrogen oxygen propellant combination. Therefore, we have to take a look at dissociation, and these are results for which we are not yet equipped to do the analysis, but we will be doing it. Let us therefore go with this background into what happens when I have a reaction, stoichiometric reaction of hydrogen plus half oxygen, let us say forming water. My aim is to find out the temperature of the combustion products. How do I do this problem? We would first like to understand what is the heat generated in this reaction, but mind you, hydrogen and oxygen are not at a standard state of 298 Kelvin, but hydrogen is a liquid, I use it as a liquid at 20 Kelvin, I use oxygen at 80 Kelvin instead of 298. Therefore, I have to first convert these two substances which are at a reduced state, reduced temperature to something like 298. In other words, I would like to take hydrogen which is a liquid at 20 Kelvin, convert it ultimately to hydrogen as a gas at 298 Kelvin. Similarly, I would try to take oxygen which is now a liquid at 80 Kelvin, convert it into hydrogen, I am sorry, oxygen as a gas at 298 Kelvin. Once I have converted this, then the standard heat of formations I can use, and what is it I can do? I can thereafter take this oxygen which now I have converted to 298 which is a gas, hydrogen which is a gas at 298 Kelvin. From this I can get water H2O which is again a liquid at 298 Kelvin, right. Now, what happens? Some heat is generated in this reaction. This heat takes the water, that means H2O as a liquid at 298 Kelvin and converts it as H2O as vapor at a high temperature Tf, and this is what I want to find out, what is my temperature. Therefore, I have to go through this process, and what is it we call temperature? If it is adiabatic, we call it as adiabatic flame temperature. Therefore, we would like to find out the adiabatic flame temperature of the products of combustion when the reactants are not at the standard state, but in a state of liquid at low temperatures, and this is what I want to do. Therefore, what is it I have to do? I have to first take this hydrogen which is a liquid, take it to its boiling point at which it is still a liquid, and boiling point maybe of hydrogen is around 22 Kelvin. That means this is sensible heat wherein I still have the liquid phase, and then once it has reached the boiling point at 22 Kelvin, I supply the latent heat or heat of vaporization and convert it to H2 vapor again at the boiling temperature itself. It is a constant temperature process, and once it has reached Tb, and we said Tb we are assuming it to be 22 at the particular pressure. Once it has become vapor, again I have sensible heat, I increase the temperature from 22 to 298 Kelvin. Therefore, heating of the liquid, conversion of the liquid to vapor and heating of the vapor to the standard condition is what is required here. Similarly, for oxygen, now I know this, if I can say oxygen is a liquid, at the temperature of boiling temperature of oxygen is around 90 Kelvin, then I convert it using latent heat into oxygen gas, oxygen vapor, then I convert at the boiling temperature of 90 Kelvin, I have to increase it to 298 Kelvin. And what is the process here? I have liquid which is formed at 298 Kelvin, mind you 298 Kelvin is 25 degrees centigrade. I have to convert it to water again at the boiling temperature of water, let us assume it is still 100 degrees centigrade, and at 100 degrees centigrade what I do? I have vaporization, that is latent heat taking place, and I form water which is a vapor now. This conversion is again at 100 degrees centigrade vapor, and then I convert the 100 degrees centigrade to something like TF. Therefore, the heat which is generated by the reaction at the standard state should be able to supply heat for this conversion plus taking the water to this particular temperature. Therefore, let us write the equation. I think this energy equation is very important, because I do not think we use propellants at always at 25 degrees. Sometimes in a cold condition, like for instance whenever we use N2O4, we chill the N2O4 end use, because otherwise it tends to vaporize. Therefore, you have to consider this, and a classic example is these low temperature propellants. That is what I thought I should do this. For can I start with the problem? Is the thing clear? All what I am trying to say is, all what we studied so far was the substance is originally at the standard state, and the products are also formed at the standard state, and we calculated the heat which is generated at the standard state, because we just said yes, we had 1 mole of H2O into delta HF corresponding to H2O, which was something like 286, and minus the heat of formation of the reactant was 0, 0, that is 0 plus 0, and we found out what is the decrease, and we said H2O is equal to something like 286 kilojoule per mole. I am forming 1 mole, therefore the heat generated is equal to 286 kilojoule in this reaction. We never bothered about the heat of this which goes into this, or the heat to calculate this temperature. Let us do it now. Therefore, let us put the data more clearly. I just put down the data together. I think data is important. We have hydrogen as a liquid, the boiling temperature is 22. We need, for this change, we need the specific heat of the liquid hydrogen. Let me put it down here. Specific heat of LH2 is required, and the specific heat of LH2 is equal to 20 joule per mole. The latent heat of conversion of liquid hydrogen to hydrogen vapor at the constant temperature of 22 Kelvin is equal to 890 joule per mole. I prefer to use mole as the unit of the matter of substance, because it tends to be simpler, because always chemical rate equations are written in terms of moles and conversions become simpler. Similarly, if I have for oxygen, the specific heat of liquid oxygen is equal to 29 joule per mole. The latent heat, that is equal to HFG, is what we normally use. HFG for oxygen is equal to 6800 compared to 890. We need two more things. We need the specific heat of oxygen as it increases in temperature between as a vapor. That means we are looking at specific heat of hydrogen as a gas, and similarly specific heat of oxygen as a gas. And the specific heat of hydrogen as a gas is equal to 30 joule per mole Kelvin, and the specific heat of oxygen is equal to something like 35. We should have had the word Kelvin here. Whenever we have specific heat, we are talking per unit temperature change. And similarly, when we talk in terms of water to this, here you are talking of specific heat of water as a liquid, latent heat of water over here, you are talking of specific heat of water in the form of a vapor. Let us put down these values. Liquid is equal to 90 joule per mole Kelvin. The conversion of HFG for water is equal to 35. Again I think we will have to check these numbers. Yes, 35,000 joule per mole, and specific heat of vapor is equal to something like 58 joule per mole Kelvin. How do I do this problem? When I have the heat coming out under standard conditions, all what we are able to write is, if H2 is at 298 Kelvin and it reacts with half of oxygen again at 298 Kelvin, I form water, 1 mole of water at 298 Kelvin, and in this case the heat of formation of water is equal to minus 286, or I get 286,000 joules of energy per mole of hydrogen reacting, right, from standard heat. Now what is happening? Let us say, let me put this in a better form. Let us, to make ourselves doubly clear, the heat given to liquid hydrogen is, it starts with 20 K, goes to boiling point at 22 Kelvin. This corresponds to Cp of liquid hydrogen into dT, plus I have HFG corresponding to the hydrogen going from liquid to vapor, plus I have between 22 to 298 the value of Cp corresponding to gaseous hydrogen dT, okay, plus let me do the same thing for oxygen. I have from 80 Kelvin to the value at 90, which is the boiling temperature, is equal to Cp corresponding to liquid oxygen into dT, plus HFG corresponding to oxygen at 80 Kelvin, plus I have going from 80 to 298 corresponding to C of oxygen gas into dT over here. Whatever I have written here through arrows, I have set this, and I am also assuming Cp to be constant in this particular region, and whenever we say Cp is a constant, we assume it is something like a perfect substance. Cp does not change with temperature. Let me not do this exercise by putting the numbers, I will just call it as H1. What is H1? So much joules corresponding to this. Maybe you all could calculate and plug in the value of H1. Now I want to know the value for water. What happens over here? What happens to water? Again it has 1 mole. I think we forgot something. See, this is per mole, per mole, per mole is all right. When I have oxygen, it is half mole here. Therefore, I have half mole because HFG was per mole. I have half mole here. Therefore, H1 should contain half mole of oxygen and 1 mole of hydrogen over here. Because mind you, we defined Cp in terms of joule per mole Kelvin. We defined the vaporization process as equal to joule per mole. If you are going to use the standard way of looking at joule per gram Kelvin or joule per kilogram Kelvin, better to convert the mole into gram or mole to mass and then use this relation. But I always find working with moles is to be much simpler. Now, when I want to use it for water, what is it I do? I again take water is formed at 298, therefore, you have 25 degrees centigrade to I still assume 100 to be the boiling temperature. If the pressure is higher, the boiling temperature will go up. Cp for water as a liquid, which we know, into dt plus HFG for water, which is given to you per joule per mole, plus I have from 100 to the value of Tf, which is the adiabatic flame temperature, into Cp for water in the form of vapor into dt. This is all 1 1 1 because I have only 1 over here. This I call as H2. Now, what I do is my heat which is generated is equal to 286,000, or rather H1 plus H2 is equal to 286,000, and the only unknown is the value of Tf, which is equal to Cph2O vapor Tf minus the boiling temperature of water. Because all other things are known, we are able to get the value of Tf, and this is how we calculate the flame temperature. What is the molecular mass? Well, molecular mass is this product here, the molecular mass is equal to 18, and therefore, you can find out the C star, you can find out the performance of the propellant. Therefore, given any propellant at any temperature, you have to convert it to the standard and then evaluate based on the difference in the standard between products and the reactant, the heat generated in the reaction, and convert the products into something like a final temperature, adiabatic flame temperature, and this is how you calculate the flame temperature or the adiabatic flame temperature. Which one? Here, see what is it I have done? I took half mole of oxygen from the initial temperature to 90 degrees, it is a liquid CpLO2 dt. Then I take half mole, convert it to vapor, it is again at the 90 Kelvin. Yeah, you are right, because we said that the boiling temperature is 90. You are right. Huh? That means this should have been at the standard at the boiling temperature of 90 Kelvin, and this goes from the boiling temperature of 90 to 298, and this is what it is. Which one?
The reaction need not take place at 25 degrees.
No, let us be very clear. You are telling me that the reaction need not take place at 25 degrees centigrade. See, we are not talking of a chemical reaction at all. What is this we are talking? We are doing some equilibrium analysis. We say that when a substance gets converted to products, that means the substance which is reacting is at the standard state, it has certain heat of formation. If I have products which is again at the standard state, the same standard state, it has some heat of formation. When I go from this structure of, let us say, substance which has some internal chemical energy, which is this heat of formation under standard condition, it loses some energy. That energy is coming as the heat of the reaction. We are not talking of a chemical reaction taking place at 25 degrees or 100 degrees or 200 degrees. This is just a case wherein we are comparing what is the heat which is required, heat which comes out, heat deficit in a chemical reaction. This is all what we considered. And what is the heat deficit? It ultimately comes as the heat of combustion, because this deficit goes to heat the product at high temperature. We are not telling about rate of reaction, that comes from a totally different source, because we must remember one thing. See, whenever we study all these things, we have never said what is the we have never said anything about rate of reaction. Let me take one example. If I were to have a tank, let us say this is tank, this tank contains a volume of let us say 1 meter cube. Into this tank I put something like hydrogen. The amount of hydrogen I put is let us say 2/3 of this I put as hydrogen, that is 2/3 meter cube of hydrogen at atmospheric pressure I put, and into this volume I also put 1/3 meter cube of oxygen. I mix the two, nothing is going to happen. It is at room temperature. What I have is H2O gas at let us say 1 atmospheric pressure 25 degrees centigrade. I have oxygen gas, half of it is oxygen, which is again gas at 25 degrees and again the same 1 atmospheric pressure. Nothing is going to happen, I am not going to get water at all. But if I were to overcome the initial barrier, what is the initial barrier I am talking of? I am telling, yes, all these two things are standard, like for instance I have a scale here, that means I am talking of something like initially hydrogen is at this level and oxygen is also at the same standard level. I need to excite it, that means I have to increase the activation energy such that it goes through this and comes back and forms a reactant here, that means I have to supply some ignition energy to it. Therefore, I put a spark over here, I create a high temperature environment, and then what is happening? Because of this high temperature I make hydrogen and oxygen react. Maybe we have to go to chemical kinetics, maybe let us see if we should do that. And then what happens? I form, therefore this reacts and form H2O, which is in the vapor state, right, because high temperature gases are formed. Then what is it I do? I cool the products of combustion into something like, I form it as water at liquid state. And now I find that the change in the energy for this is corresponding to heat of formation of the product minus sum of heat of formation of the gases, and therefore if the product is at the same standard state as this, the energy liberated is equal to 1 of heat of formation of H2O, which is in the liquid state, minus 0 plus 0, and here I have minus sign over here, and this is the heat which is liberated. I am not talking of reaction taking place at any temperature. All what we say is heat of formation is at standard, products are standard, so much heat is formed, and what is the mechanism? This heat goes to increase the products to the higher temperature, and if the reactants are at different temperature, again it helps to either if the reactants are at higher temperature, they will give you more energy itself. In fact, if we were to take a case, let's do it right away. You know, in most of the rockets, liquid propellant rockets, as we will see when we study liquid propellant rockets, you know, you do not inject at, let us say you have the case of, let us say we have monomethyl hydrazine as one of the fuel, you have N2O4 as a oxidizer. You mix the two, you burn them, generate hot gases, and if you calculate the temperature may be something like 3200 Kelvin, and this hot gas is expanded through the nozzle. What are the products you are getting? You have carbon and hydrogen, you get CO2, you get CO, you get maybe some dissociated species, you get water, you have OH, these are the products you get. Now, you know, the chamber runs hot, therefore you rather take the fuel, instead of injecting it into the chamber, I rather preheat the liquid MMH which is coming, instead of it being injected at room temperature of 25 degrees centigrade, I inject it at something higher temperature of something like 80 degrees centigrade. I use it to cool the wall and then inject it. Now it is at a higher temperature than 25 degrees centigrade, therefore it has higher energy, and this energy also contributes to this. Therefore in this case I get H1 will be negative because that is the this is bringing in more heat into the combustion, and I have heat of formation which helps this. Similarly, N2O4 may be at a temperature of something like 5 degrees centigrade instead of being at 25, therefore heat has to be supplied to make it 25 degrees centigrade, heat has to be removed to make it 25 degrees centigrade, and therefore I have excess heat here which helps in increasing the energy of combustion. In fact, we are using regeneration, we are reusing the heat from here to be able to do this, and such type of cooling is known as regenerative cooling. We will consider this. Is it all right? Now let us go ahead. Therefore, we know how to calculate for a different set of propellants which are away from the initial, which are different from the initial standard condition, what is the heat liberated. Let us also quickly do, since we did hydrogen oxygen, let us take a look at, maybe I have hydrogen oxygen reaction which is stoichiometric giving me H2O, and this has a fuel to oxidizer ratio or mixture ratio which is oxygen divided by fuel, which is equal to 16/2, which is equal to 8. What is the molecular mass of the products? (18), right? 2 plus 16, 18 gram per mole. Supposing I were to consider a fuel rich reaction, H2 plus, I cannot give half O2, maybe I give quarter O2. In this case, what is going to happen? Let me just have a something like a guess over here. I cannot form H2O because I cannot have, I have only half of oxygen, therefore I form half H2O. No, yes, half H2O because I have half of oxygen here. And what happens to the balance oxygen? I get the balance hydrogen. What is there is 1 minus half hydrogen which is left. Is it all right? Please check. I am just putting hydrogen plus this. What is the mixture ratio of this reaction? Is equal to 1/4 into 32 divided by 2, which is equal to 4. Is it all right? What is the molecular mass of the products in this reaction? I have half into H2O 18 plus half into 2, which is equal to divided by half plus half, which is 1, that is 1, which is equal to 9 plus 1, which is 10. What is the energy liberated in this reaction if it was of this type, stoichiometric? What is the energy liberated in this reaction? Let us put that number down also. What is the heat of formation of water? Let us go back, 286. Therefore, the heat of reaction in this case is equal to delta heat of combustion is equal to 286 kilojoules. What is the heat in this reaction? 0, 0, 0, all at standard state, which is equal to 143 kilojoule. 286 by 2, 143. Now we consider a fuel rich condition. Let us consider the reaction of H2 plus O2 giving me H2O plus half O2. I am just assuming this, mind you, we have to do an equilibrium analysis, chemical equilibrium, and find out what are the constituents, but this may not be very bad to begin with. Therefore, what is the mixture ratio now? Yeah?
16.
Yes, correct. 32 by 2, which is 16. What is the value of the molecular mass of the products? Yes, we are talking in terms of 18 plus 16 divided by 1.5, is it all right? 18 plus O2 is 32, 16 divided by 1.5, this is equal to 3 by 2 into 44, that is equal to 66 gram per mole. Am I all right? Divided by 1.5, yeah, you are right, 2 by 3, 88 by 3, 88 by 3 means 2, 6, 24, 28 gram per mole, 24, 2 by 3 into 44, 34, I am sorry, okay, which is equal to 68 by 3, 23. This is for oxidizer rich, this is for fuel rich, this is for stoichiometry, and let us now compare whatever we have done, we can revise it. What happens to the molecular mass as we go from fuel rich to stoichiometry to oxidizer rich? We find that for oxidizer rich is 23, for fuel rich it was around 10, for stoichiometry it is 18, therefore molecular mass is least for the fuel rich condition. We find that the heat release comes down when I go from the stoichiometry to this. The heat release for this is again the same because oxygen does not matter at all, it is again 286 kilojoule for this reaction. And but if I were to put it in terms of per unit mass or per unit mole, I have half mole increasing over here and therefore Q per mole comes down, and this is what we decided. Let us plot that also. Why leave it halfway through? What is it we get for the hydrogen oxygen reaction? We get the molecular mass as this is stoichiometry, this is fuel rich condition, no, fuel rich it is less, increases over here. The Q value, stoichiometry, this mixture ratio here, the total heat of the reaction versus mixture ratio, here it is constant 286, here it drops. If I were to put it Q per mole, mole keeps increasing in this direction because I add more and more oxygen, and therefore if I have to plot Q per mole, this constant will now become, and this is all what we learned, and therefore it is better to operate it under fuel rich conditions. This is all what we said. This is an example of hydrogen oxygen. We learned how to calculate the temperature. Let us now go to the next part, namely how do I calculate all these things supposing I were to consider chemical equilibrium. What do you mean by chemical equilibrium? At a given value of chamber pressure, at a given value of temperature, how do the different products of combustion, how are the products, can they exist in equilibrium? Can the products exist in equilibrium? What is the composition? Supposing I react hydrogen plus oxygen, is it that only water will be in equilibrium, or is it hydrogen will also be in equilibrium with it, and if so, how many moles of water, how many moles of hydrogen, how many moles of H and all can stay together at the specified value of pressure and temperature? And this is a much better way, rather than assuming hydrogen is more reactive and therefore first it reacts and then carbon reacts. Why not you do the real analysis? And this is what we say is a chemical equilibrium analysis. To be able to do the chemical equilibrium analysis, we must first be clear what do we mean by equilibrium. I think we talked over it in one of the classes. What do you mean by equilibrium of a substance or a system being in equilibrium? How would you look at it? what do you understand by equilibrium? How will you define it? I think we should think over it. Yeah, how will you define it?
Chemical equilibrium, there should be no reaction.
There should be no reaction. But in this case, let us say first a general example. Supposing we consider this room as a system, and let us say this room is beautifully insulated, nothing can come in, no power can come in, no mass can come in, nothing will come in. And what is the system we are considering? The system is maybe all these lights, maybe all of us, maybe these chairs, these are the attributes of this system. Therefore, I consider this room as a system, and then we say it is totally isolated. That means I consider an isolated system. I allow the attributes of this isolated system to be there for infinite time, long time. What is going to happen? No change is possible, everything is finished, all of us have spent such a lot of time, no air, nothing, all of us are in the dead state. And this final state of a system wherein no further changes are possible is what we call as equilibrium. No more changes are possible. Therefore, the concept of equilibrium is very profound in thermodynamics. We tell ourselves no further change in the state of a system is possible. And why do we say that? Because nothing, you have prevented anything from evolving. Maybe for some time it evolved and then it stopped or something, but afterwards there is no change possible. And therefore, this final equilibrium dead state in which no further changes are possible, we call it as equilibrium. And so also, but even though I say it takes infinite time, for gases to come into equilibrium, it takes a few nanoseconds or a few milliseconds, it reaches that state. Therefore, it is not necessary that I allow infinite time, but to be able to appreciate the problem, well, an isolated system left to itself for long time reaches a state of equilibrium, right. In what way is the equilibrium related to the performance analysis in a rocket? Like, let us first see, a rocket consists of a combustion chamber and a nozzle, and in the combustion chamber the propellants are injected and they burn together. The flow velocities are very small, and therefore, you have lot of time for the chemical reactions to occur and the products to go into equilibrium. The gases which are generated or the products of combustion from the combustion chamber flow through the convergent divergent nozzle. In the convergent portion, the flow accelerates from very low velocities to the throat wherein the Mach number is 1, and in the divergent the flow accelerates further to supersonic speeds. Therefore, in the convergent portion you have time for the reactions to occur because the flow is essentially at slower velocities, whereas in the divergent the time for reactions is small because the velocities are large. In addition, if you go to the if you look at the temperature distribution in the nozzle, here you have the convergent, you have the throat, you have the divergent. In the flow expands, or rather the temperature keeps falling along the length of the nozzle. Therefore, what is it we see? In the convergent we have large amount of time, or the residence time is quite large for chemical reactions to proceed further, and the temperatures are also reasonably high because the high temperatures enter the convergent, whereas in the divergent by the time the flow reaches the divergent the products have somewhat cooled down, and further the time for reactions is not sufficient. Therefore, in the divergent where the residence times are small and the temperatures are rather small, what is it we get? The further reactions are not possible and the products of reaction sort of remain the same as earlier, that means they remain frozen. In the convergent, however, since there is some time for chemical reactions to occur and further the temperatures are high, the composition keeps shifting towards equilibrium, or rather we say in the convergent you have shifting equilibrium and in the divergent you have frozen composition. Therefore, we look at the nozzle and say in the convergent portion you have shifting equilibrium and in the divergent you have frozen flow. And compared to what we have been doing in nozzles previously, namely we have been looking at the specific impulse of a rocket, and what did we do? We assumed gamma to be the same in the nozzle. We looked at the molecular mass of products in the nozzle to be same, or rather we had assumed frozen composition for which the specific impulse was derived as a function of mixture ratio. We found that the maximum specific impulse occurs in the fuel rich region, and therefore we had what is shown by the dark line over here, namely maximum specific impulse in the fuel rich region, and also we had assumed a frozen composition. If on the other hand we were to assume a shifting equilibrium, that means flow equilibrates or the chemical reactions reach equilibrium both in the convergent and the divergent nozzle, because chemical reactions occur further, more heat is generated, you have higher values of specific impulse, and the specific impulse plotted as a function of mixture ratio under shifting equilibrium conditions, that means the flow shifts towards equilibrium, is shown by the dotted line. But in practice we saw that in the convergent you have shifting equilibrium, in the divergent you have sort of frozen flow, and the specific impulse is expected to be in between that of shifting equilibrium and frozen flow, and this is what is also achieved in practice. However, it should be noted that this is not true for all propellants. The propellants which generate products which are more reactive, it could be that you have more of shifting equilibrium, and essentially if the nozzle area ratio is small, the flow could be dominated by shifting equilibrium, whereas if you have a large nozzle, that means a nozzle with large area ratio, the frozen flow could dominate in the divergent. Therefore, to conclude, we find that in the nozzles we have both shifting equilibrium flow and frozen flow, and these concepts are useful for the analysis of performance prediction in rockets. Thank you.